Okay, so this is going to be a discussion about electric fields. So let's say that we have some sort of charge Q. And to that situation, we add another charge. Let's call it charge little q. Okay, so down here we'll have charge Q. And let's make it positive. And then we're going to add charge little q at some other point. We can say, well, it's point P. And so they are going to be some distance apart. I'll just denote here. And we'll call this distance R. Okay, so they're going to be distance R apart. And so what's going to be the interaction between these two charges? Well, if little q is also positive, then they're going to repel one another. So there will exist a force. And so if both are positive, then they will repel. Okay, so I could draw maybe my force diagrams in, let's say, blue. And so there's going to be a force in that direction, a big Q on little q. And so we can now understand how these charges are going to interact. Now, let's try to quantify a little bit about that force. So we could say, well, our force here depends on a few things. It depends on the two charges, first of all. If we have a larger big Q, then there'll be a bigger force. As well, if we have a larger little q, there will be a bigger force. Until we get a real equation, we'll just stick with a proportionality. So as one of these q's increases, the force between them will also increase. Okay, now as r gets bigger, the distance between them gets bigger. Well, then we can determine experimentally that the force between them gets smaller as r is squared. So we have this relationship between the charges, the distance between them, and the force. If we want to turn this into an equation, then we need it to be exact for the unit system that we use. And so experimentally, we could determine the force, the charges, and the distance, and determine that we have some proportionality constant, and that's K, or Coulomb's constant. Now, as well, we want to recognize that the force here is a vector, and in terms of what direction it's pointed in, we're also going to want to define a little r hat vector. And that's our unit vector for the direction. And that direction is going to be from big Q to little q. Say, well, and that's in the r hat direction. Okay, so that's our equation for the force that's being experienced by little q due to big Q. Now, just a quick note about the units. The units for Coulomb's constant. So the units for K are equal to newtons times meters squared per Coulomb squared. And if you look at that in the context of the equation here, it makes sense. the Coulomb squared cancels the 2 coulombs in the equation, and the meter squared cancels the units in the r squared, and so you're left with a result in newtons for force. Okay, so the other thing we can talk about is the fact that we could have put this little q anywhere in the area around big Q. We put that charge anywhere in that vicinity, and there's going to be a force, an electric force caused by big Q. So there's something, big Q is producing something that allows it to affect any charge in the area. And we call that an electric field. So there's an electric field in the area around big Q. And we denote the electric field with big E. And the electric field is defined by, we could take a test charge, what we call a test charge, and we could take that test charge and put it here and see what happens. And if we put a test charge there that's positive, it's going to experience a force in that direction. If we were to put a test charge over here, it would experience a force in that direction. And so on and so forth. We can put a charge here, and there'd be a force in that direction. So what we're doing here is mapping out the fact that there is an electric field in this surrounding space, and we can get a sense of its magnitude and direction by using little test charges. And so we can use this to define the strength of the electric field. So the electric field is going to be equal to the force experienced by a small test charge divided by that test charge divided by Q. And that gives us, because we've got an equation for force already, well, that's going to give us an equation that is, well, we've got our constant, but then the 2 little q's cancel. So it'll be kq over r squared in the direction of r hat. And that's in newtons per coulomb. Okay, so now we have a way of defining the electric field in the area around big Q. Now, it's important to note here that the electric field is a vector. So there is a direction. And remember, every time we've placed a test charge, which by convention are always positive, so we place a positive test charge anywhere in that region, we get a magnitude, which is the strength of the interaction, and we get a direction. And if it's a positive and a positive, that direction is away from the large Q. Okay. Now that's the case between 2 charged objects. What if we had many Q's? What if there exists many charged objects? So we could say, well, let's put a bunch here. We call this big Q1, Q2, Q3, and we could draw as many as we like. Okay, and we want to know, well, what's going on at this point? We'd say here's some special point to analyze, and we could ask ourselves, well, what's the electric field at that point? how do we work this out? Well, we just look at the individual contributions from each of these charges. So we could look at the electric field that is caused by Q1. And so we're going to know that we have an electric field caused by Q1, and it will be in that direction. In addition, well, we could make this even more interesting if these weren't all assumed positive. We could say with this one's positive, this one's negative, and this one's negative. Okay, so if that's the electric field caused by 1, it's a vector, then what about the electric field caused by 2? Well, in that case, the field is going to be in this direction. Okay. So this is the electric field at that point caused by Q2. And then lastly, we can do the same thing for Q3. Okay, electric field by 3. All right, so we've got a combination here of 3 charges resulting in a field that's going to be the result of summing all these up. And so we're going to end up with some net that's going to be, well, it'll probably end up being, we've got a component. We're going to have to think about how these break into components. So we're going to have a component here and a component here for this electric field, for example. And then in this case, this isn't drawn perfectly, but these should be symmetric. So we'll try to fix that a little bit to look a little bit more symmetric. Okay, so the idea there is that the y components, if we want to think about this in terms of, if we were to draw like a y-axis there, say, well, this is y and this is x. So our y component here from E2 is going to cancel with the y component of E3. And so they will have a resulting net electric field that is to the left. And then that will have to balance with the electric field to the right of 1. But 1 is a bit farther away, so it'll be weaker. And there's also not as many as 1 and 2 together, or rather 2 and 3 together. Okay, so we'll end up with some net like this. So we'll have some sort of net electric field at that point. And that's the combination of all 3. So this is the superposition principle, where if you have multiple fields produced by multiple charges and you want to know what is the overall electric field at a point, you just add them all up. So if you want to know the overall electric field, you're just going to add up all of the electric fields. Okay, and so if you're looking for the resulting force, you can add up the force contributions from each three individually, or just go straight from the net field to the resulting force. Okay, so that's electric fields. Now, one thing we want to touch on is being able to work with some simple examples and drawing field lines. That's going to be up next. So let's say that we've got some example where we've got, well, first of all, I'm going to take a copy of this and we're going to duplicate it, and we're going to move some of these down here. Let's just talk about the combination of these two things together for now. Okay, so we've been talking about, them being equal a lot, but let's make them unequal. Let's say that this has a value of not just 1, we'll make it 3. And maybe the other one will be, we'll just keep that as 1 for simplicity. Okay, so we've got a +3 and a -1 charge. Do a quick example here. Now, what's going on if we choose a point really close to 1? Well, in that case, we're going to have an overall force and an overall field that's going to be much more strongly influenced by the -1. And so if we're looking at, well, what kind of field do we get next to a negative, we're going to have an electric field that is in this direction. So that's what the field is going to look like at that point. Well, there will be a contribution from the +3 wanting to have an electric field in this direction. It's so much farther away compared to the -1. The -1 is going to win out here. We're not using exact distances, but in principle, this should work out, because this distance from the +3 to the point is, remember, subject to the 1/r² law, which means the intensity is falling off very quickly. So if you're really close here, the -1 wins out. However, as you move farther and farther away, then you're going to have more and more impact from the +3. And so the +3 is trying to say that contribution is going to create an electric field that's in this direction, and the negative is going to give a contribution that's in that direction. So the net will eventually turn out to be in the direction to the right. And that's because, when the distance is far enough away from both of them, the +3 is going to have a greater impact because it's a larger charge. There comes a point, which you can find mathematically, but there comes a point where the +3 starts to win out and the direction of that field flips. Now, if you're really far away, we could say, this is not linear, this is like very far. So at some point, you're very far away, draw a point here, and you could say, well, what does this combination look like? And well, you're definitely going to have a field that is towards the right, and let me just draw this. Okay, so you're definitely going to have a field that is to the right. And as well, these two charges are going to, from a far distance, so at this point, I'm just going to move this over just a wee bit. Didn't mean to take you with me. Okay, very far. So the small distance, relatively speaking. So the small distance between +3 and the -1 doesn't really matter. It's just going to look like a +2. Okay. So you can also draw field lines to describe this situation. Maybe we'll move this just a touch over. Okay. So if we wanted to draw out the field lines to get a sense of what this looks like, then why don't we do it for the case here? So we can draw out So remembering the field lines are only going to be an illustration. They don't represent something that's physically real. It's not physically real. Field lines are just going to be a way of getting a sense of what's actually going on. It's not actually going to be like a physical object. We could draw as many or as little as we want. Okay, so the first one we can draw is, well, if we pick a point in between these two charges, if we pick a point here, well, the electric field caused by the positive charge is going to be in this direction. In addition, the electric field caused by the negative charge will also be in that direction. So they add together, and they're going to be a nice, smooth field line going from one to the other. And we can add an arrow to make the direction really clear. And we imagine ourselves putting a positive test charge on that line. In fact, that's exactly the trajectory that'll follow in this case. Okay. So what about other lines? We could pick a point here. Well, what's going on there? Well, the largest contribution will be from the plus, but there'll be a small contribution from the negative as well. And so we'll probably get something that's mostly like this, and then we're going to go a little farther away. You know, it's not going to be purely like this as it would be if it was only the positive. We'd probably get some contribution from the negative, so it'll be pushing it over there. And then around the middle point, we're going to get, you know, this point here and this point there, and eventually it's going to look like that. And so we can redraw all of these individual test cases as a field line that's continuous from here up and over. That's not so good. We're trying to be symmetric about this. That's better. And we've got a direction associated with that as well. We'll probably draw another one. That's not terrible. And so this is going to be going on both sides. Okay. And some of these we'll kind of see they go probably outside of the scope of this drawing. Sorry, I drew these arrows in the wrong direction. There we go. All right, so we can draw out all these field lines and get a representation of the electric field in that whole area around the charges. And as one of the charges gets bigger, then they will have a larger impact, especially near to them. So this shape can be quite complicated depending on the combination of charges. Okay, just a quick point about how charges interact with these field lines. So let's imagine that we have some area where we have a constant electric field. Okay, so we've got an electric field in this area and it's uniform. So if we have straight electric field lines, a positive charge released at a point in the field will follow the lines. Now there's a couple of subtleties to really be clear about here. So if we take some charge and it's positive and we just drop it right there, it will move there. There'll be a force on it in that direction and thus an acceleration, and therefore it will move up here, continue on, be there, and continue on. That's how it's going to move. And of course, remembering that these are illustrative, if I put an object that's got a positive charge here, it will have a force on it like there and move there, etc. Right? There is an electric field in between the lines. They're only there as an illustration. Okay. Now, that's in the case where it's just been released. If it had some velocity, some initial velocity, well then there'll be a force on it and there'll be a combination of motion depending on initial conditions and the impact of the electric field. Now, things get a lot more complicated if we were to have some sort of curved field. Now, if we have some sort of curved field, could be near the edge of a capacitor, all sorts of things, complicated electric fields. So if we have curved electric field lines, and we put the same positive charge, well, there's going to be a force, right? It's going to be a force, and there's going to be an acceleration, and that's going to be in a direction. What direction will it be? Well, it'll be in a direction tangential to the line. But it will immediately, but the charge, just to be clear, but the charge will immediately leave the line. So in this case, trajectories of particles will be very complicated. Right, so we might imagine ourselves, okay, well, let's let's take some charge, we'll put it right there. So at that moment in time, we have a force that's aligned with that tangential direction, and so it'll then move here. But then by the time it moves there, you know, it was moving in this direction, but now the tangent to the field is now in this direction. So now it's going to curve, you know, in a different direction, and then as it moves, again, it's going to be, you know, the field is changing, so the force that it applies to that charge is going to change at every moment. So this turns out to be a very complicated trajectory to trace back. Okay. And so that's it for this introduction to electric fields.